All right, here we are once again. So we are doing text classification today. So last time we created vectors for text, and then we're able to use those vectors to find similar documents. So if you created a vector for a document and a vector for all your other documents, you put them in vector space, and then you can use Euclidean or cosine distance to find the similar ones. So that's what we did. But we didn't do any machine learning last time. So this time we're going to move to machine learning, and we're going to take those vectors that we got last time and modify them a little bit so that we can put our documents into buckets. And this time the buckets we're going to use are whether a tweet of mine is about movies or not about movies. And so the tweets are on the GitHub page, and you can download them, or you can download your own tweets or any kind of data you want. Doesn't really matter. So here we go. So we're doing our normal stuff here. If we're going to import a bunch of stuff, we use type hints because that's nice. We just like last time, we're implementing our BERT. Now we're going to use Tensor Board this time, and Tensor Board is a TensorFlow thing, but it works really well with PyTorch as well. So we're going to do pip install, or however you like to install things. And so then once we've got our Tensor Board, and the value of Tensor Board is that you can plot your learning as it goes. So before Tensor Board, you had to like make your own plots, or just kind of look at it on the console as it went by. And so this Tensor Board is just a beautiful thing. It lets you see your plots, and it's nice and easy. So here we're going to do, once we've installed Tensor Board, we're going to do from torch.utils.tensorboard import summary writer. And that's how we're going to do the plotting. But let's first get to data. So these are just a bunch of stupid tweets that I write, and I downloaded and put them in a file for you guys. You guys and all y'all. So let's see. So we've got, I just load my tweets. That's all nice and easy. But one thing we're doing here is we are downsampling, since what we're going to do is we're going to classify whether my tweet is about a movie or not. Now, I tweet about movies a decent amount, or I used to, but obviously not all the time is it about movies. It's a very small amount of the time. So what we're going to do is we're going to downsample, and this gets us into this issue of imbalanced classes. So machine learning works best when you're putting things into buckets where the classes are pretty much balanced. And there's a lot of different methods to get around that. I taught a whole course on that at one point. But in this case, we're going to do the simplest possible thing. We're going to downsample, which means of the tweets that are not about movies, we're going to delete them with some probability 0.95. And so when we do this, we run our training tweets downsample. So it takes in our list of tweets, all tweets, which is, which we got here when we just loaded in a data set. And it says, okay, for every tweet, is it a movie tweet? Now, of course, that's the thing we want to classify, but here we're just here to learn. Normally you'd have either people hand label things, or you'd have some other way of labeling something. But we just do the simplest possible thing, which is movie tweet, returns a bool, and just says, is lowercase movie in the tweet? Lowercase. Because, of course, we're just demonstrating. And so if it is, add it to the data set. And if not, only add the tweet to the data set if with probability 0.05. If random.random greater than 0.95. So when we do that, we get 45 positive tweets about movies out of 101. Okay, now that's, of course, a very small learning set, but we're just learning how this works, how to do classification for text in natural language processing. So we want to do something simple we can get our head around. However, we want to do something simple we can get our head around, but one of the most interesting aspects of this is that you could use a data set that is so large it doesn't fit into your memory. In fact, you generally will. So you may have 100 gig of documents you want to classify. So what we're going to do is we're going to use something called a data set to represent our data set, and this is a efficient way to load the data into PyTorch. So we do from torch utils data import data set, and we're going to create this thing called a tweet data set, which just inherits from data set. Now this one keeps everything in memory, so we just pass in the tweets. But you'll see down here, I commented this out, you could use an iterable data set, and basically what you would do, you would define an iterator, or in your iter, you would load in your file, or however you want to do it, and then, of course, when you're reading a file, you're not reading in the whole file at once, you're just reading bit by bit, and you just do a little yield here, just like you're reading a file. So that's how you do that, but of course in our case it does fit in memory. So we just take in a list, and we have a length, so it may ask how long is this thing, and we just say, here, get this item. And this get item is useful because later on we're going to use some machinery that shuffles for us, and this is nice for that. Okay, so we've got our data set, which is kind of an abstraction around our actual data, and now we need something called a data loader, which is going to deal with that data set abstraction and pass the data into our machine learning mechanism. And so these are really nice abstractions because, once upon a time you had to do all this yourself. Let's start at the bottom here. So what we have is a data loader. And this data loader, of course, is going to pass our data into the learner. And the data loader takes our tweet data set with training tweets, just like we saw a minute ago. And it's going to take a batch size. And so, of course, most of us know that in machine learning, we don't process one thing at a time like we did in the last episode. We process many things at a time, and that allows us to put many things on the GPU at once. And then we can take advantage of the efficiency of that. I mean, in this case, we're not using GPU, but you still want to use batch size to smooth out the gradients and such. So our batch size is just 20. Usually you want to pick like the biggest batch size that'll fit in your memory, which with BERT is actually pretty small because this is such a huge model if you have the kind of GPU that most of us have. But here we are. And then shuffle. So what we want to do is we're going to run this data through our learner multiple times, and each time we do that, we want to shuffle the data afterwards so that it doesn't see the same tweets all batched together. And now we've got our data set, but on every time our tweet data set, here it is. But on every time we process that, every time we create a batch, we need to do some stuff. Like we saw last time, we need to put it into tokens, and then we need to put it into IDs, and then we need to put it into a tensor. So that's this preprocessed batch. So now that brings us back up here. So preprocessed batch. So it takes just a batch, which is just a list of tweets, which of course comes from our tweet data set. It's going to pull those out of batch size automatically behind the scenes. So we get that, and this is what we did last time. We tokenize. We do this is a little different though. We find the max length, so we're going to get a batch of 20 tweets at once. And what we want to do, of course, is convert that into a tensor where the axis 0 is the number of tweets in our batch, and axis 1 is the number of tokens. But we want to make that tensor as small as possible, so we need to find the max length of the tweet in the batch so that we can make our tensor that size. And then here we are. We're going to create our tensor. We're going to create this input of max of batch size and then max length, which we computed over here. So if 4 tweets are of length 10 and another is of length 100, and then all the other ones are in between, then this max length will be 100. And we're also going to mask the data, since when we pass in the data we're passing in data of a tensor of the same size. However, the tweets are of different lengths. So what we do is we say, okay, if there's a token in that position, we want to say, yes, use it. Otherwise, don't. So, so here we are. So what we do is then we take our tokenized tweets after we've done that here, and we convert the tokens to IDs just like we did last time, and we make a tensor just like we did last time, and then we put it into our tensor. We put it into our big tensor that we created, which is right here, torch.zeros. And then we do the same thing with mask, but we just set it to 1 for the number of tokens. And of course, we need the labels here. And we saw earlier that this labeling function is just really simple. You just call your isMovieTweet. And of course, this is not realistic in real life. If you could label things this easily, you wouldn't need to do machine learning. But here we are. And then you create that, put that into a tensor. And then you return all this junk here. So you get your data, which is this thing, your actual data, and then you get your mask data, then you get your labels, and then we go ahead and return what we got in, because we'll use that later just so we can see what the tweets actually were for a particular batch. Okay, so that is how we run our data. All that is to set up so that we can pass our data in to our learner. And so now let's define that learner. So we've got our classifier here. It's a PyTorch module. So let's see. You've got a classifier here, and then what you do in a PyTorch module is in the init function, you're specifying all the parameters that you're going to learn of your module. So we're going to pass in an encoder. And this is going to be a BERT model. We're basically just going to pass in that model we used last time and set it to self.encoder, because we're encoding each tweet into a vector. But now we want to do something a little different, or a little additional on top of that, is we want to specify what class is it. Is it a movie or not? So we put this linear thing on top of it, and it just says it takes the encoder.config.hidden size, which is like 762 or something, and passes and converts it into a two-dimensional output, a score of yes or no. So then when this classifier is called, then this forward function is automatically called, and we pass in our input data and our mask data, and we get back a tuple of torch.tensor and, I misspelled that, torch.tensor. So, but it's weird that didn't matter, but so it goes. Type hints in Python are really only used for type hint checkers. That the compiler doesn't care. So it's mostly for human eyes is what I found. So forward is called when you call a model instance. So here's where we called our encoder, just like last time. But this time we're passing in an intention mask. So last time we called, BERT, and we passed in the data of one tweet. But remember, we had to make it a 1 by length size, and that's because normally you're in batch world, and here we are in batch world. And this time we're passing this an intention mask in addition, because the tweets are of different lengths, as we talked about before. And we get our pooler output, just like last time. We just rename it to vectors because it keeps life easy. And then, though, we want to classify it. So we say self.classes, which is this linear thing. And it's basically just a matrix in there. And then we pass it and we get our logits. This is going to be shaped batch size by 2. Now, in deep learning, the most difficult thing is not the math or the theory or GPUs. The most difficult thing is knowing the size of your tensor. And so you have to put these little comments in everywhere. All right, and so then we just do a little softmax on top of it, and we do a log softmax because later we're going to pass it into a negative log likelihood error function. And if we do this log softmax, it takes care of the numerical instability for us. So basically we get the outputs of the predictions of whether or not these tweets in the batch are movies or not, and the actual vectors themselves. And we'll use those actual vectors themselves in the next video where we plot them in three-dimensional space and see how they cluster together. Okay, so now we got to create our BERT model just like we did before, and this is all the same. And now we pass, we got our model here, and we pass it into our classifier as we saw here. And then we say, okay, we're going to train this guy or gal. We don't know its gender, but we're going to train it. And we get an output of it when in Jupyter Notebook here. Now, we set up our optimizer. So this is interesting. So we've really got two pieces here. We've got the core BERT model that we used last time, and we've got the head we put on top of it, the thing that converts it from that long vector we had down to 2 dimensions, so we can make the classification. So so what we do here is we want to break them up and have 2 different learning rates, and the reason for that is BERT is trained on a whole bunch of stuff, and we want to customize it for our use case, but we don't want to change it too much because it's been through a lot of training, and we want to make sure we maintain everything that was learned. So it's a little bit like humans, right? So if you call your insurance company and they say, oh, actually you're wrong about some arcane aspect of how your insurance works, you're likely to accept that. So that's fine. You've had a relatively high learning rate. But if someone were to tell you, hey, it turns out that if you drop objects, they don't fall to the ground, you were wrong about that. Well, you're going to be less likely to believe them. You're going to need more evidence because you've had more training in life that tells you that when you do drop objects, they fall to the ground. So that's why we use kind of a rough analogy of using a lower learning rate for BERT. Okay, that's all nice. So now we train our model. So we create our summary writer. Remember, that creates those nice graphs we're going to see later. And what we do now is we're just going to run it for epoch, and epoch is a pass through the whole data. And remember all that work we did before about setting up our trained data encoder? Well, that's all good because where is that thing? Here it is. This is very good because now all we can do is we can just loop over it, and we know now that the trained data encoder returns that tuple, which is this input tuple, which is the input data, the mass data, the labels, and the tweets. And as you run it, it's just going to keep giving you batches. That's its job. And then when it ends, this loop ends, then you do the next epoch. It'll shuffle, and you keep going until you're tired. So now we get our output from our classifier. We pass in the input data and the mass data. And then we get a loss. So I mentioned before we use the negative log likelihood of the labels and the log softmax, and we get some loss. Now there's a interesting thing about PyTorch. You have to explicitly zero out the gradients because they accumulate over time. That's just a little thing to know. And then what we're going to do is we're going to compute the gradients with respect to the parameters. So we're going to set loss backwards. And that basically runs the machine learning. It runs the actual back propagation algorithm, which is the chain rule of calculus, essentially, up through the error function to minimize the error to change the parameter values. Now, these parameter value changes are computed here, but to actually apply them, we used a step function. And now recall that we set the BERT optimizer to have a smaller step than the head optimizer, the learning rate. And that's because, you know, we don't want to, someone tells us that you drop objects, they fall to the sky. We don't want to believe them right away. We need more evidence. Okay, and we print out the loss just for fun, and then keep track of how it's going. And then we can actually make the predictions by taking the argmax and say, okay, is this tweet about movies or not? And we can get the labels, and we can get the batch size, and we can compute the accuracy, and this is all, we can just print all this stuff out just so we can see how it's going. There's predictions and the labels and the accuracy, but really what matters is adding these things to the summary, which is going to print them off in, or create our graph in Tensor Board. So we're going to show our loss train and our accuracy. And so when I run this, or when you run this, you'll see, you know, it prints off your predictions and then your labels and then your accuracy. And this should, you know, get better over time. Accuracy 0.55, initially it's just predicting nobody is about movies. Eventually we should see it's starting to say some of these are about movies. Now this, you can look at this and it's kind of useful, but what's really useful is looking at it in Tensor Board. But first let's save the model after we trained it. And this training takes like 5 minutes. You know, it's a small data set, huge model with the BERT, but small data set. I only ran it for 10 epochs. Yeah, so we'll just save the model, and then you can print out the parameters just to kind of see all the different things that's in your model here. It's quite a bit of stuff. It's worth going through it at some point and saying, okay, that's that. But here we're going to look at in Tensor Board. So you go into your logdir, which is, you go into your directory, which you specified up here, data-dir, when we created our summary, which was right here, data-dir. So you go in there, and you do Tensor Board logdir, and you get something that looks like this. So here we are in Tensor Board, and it prints our accuracy as we go. And this is really important because it tells you when to stop training. So this is just, normally when you do machine learning, you convert the data into three partitions: the training, the valid, and the test. And so the valid is the validity data is the validation data is just so you can run your model on different data it hasn't seen before. And then your test is so you can know at the very end how well your model is going to generalize after running it on multiple different models during your search for your models. But in this case, we're just using the training data because this is a short 5-minute video that's probably longer than 5 minutes. And so we see our accuracy goes up. That's always nice. And our loss goes down. And you can like change the smoothing on this, and it's all very nice. And in the next video, we'll see how we can use Tensor Board in even a better way to plot the different vectors in 3D space. So, and then here's a little picture here, just so you have it. And yeah, so that's about it. And as I mentioned, in the next video, we're going to plot these in Tensor Board in 3D space and just kind of get a glance of what things are looking like. And so we want to just write out these vectors. So I run through, we turn the classifier to eval. Like some models have dropout and things that work differently under train and eval. And so we want to turn off dropout. And we're basically just running through the model again for each of our tweets, putting them into into our vectors and just pickling them because we're going to load them up later. So that was that. So what we did this time is we actually did learning. So we took the vectors from last time, or the method to get the vectors from last time, and we added another piece to it where we say, okay, now I don't want to find just similar documents. I want to put my documents into buckets. And in addition, I want to put them into buckets based on some labeled training data I have. And so now we've moved to learning. So that's great. Thanks.